What if the most dangerous part of a suspension bridge isn't what you see? Because inside those main cables, which look like solid metal, there's a hidden structure made of tens of thousands of wires, each one vulnerable to destruction, even from a single drop of salty fog. So why doesn't a bridge weighing thousands of tons collapse every single day? And what happens if moisture gets inside the cable where nobody can spot it? Stick around until the end. You'll discover a secret even bridge engineers don't talk about. The classic example, the Golden Gate in San Francisco. It's got two main cables slung over the towers and anchored into massive concrete blocks in the rock. Each cable's diameter? About 37 inches. We're not talking rope here. This is basically a steel column so thick you'd need 2 or 3 people linking arms just to wrap around it. Inside? 27,572 individual wires, compressed into a perfectly round bundle. Unwind all those wires and lay them end to end, you'd get roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. The weight of just one cable? Close to 24,500 tons. That's comparable to a small cruise ship or a few hundred fully loaded semis. Why use so many individual wires instead of one giant solid rod? Here's the thing. Steel works great in tension, but it doesn't handle defects well, especially in large cross-sections. When an element consists of thousands of independent wires, each one can play a little, taking on a bigger share of the load here, a smaller one there. If for some reason a single wire corrodes or weakens, its share in the overall strength is minimal, and you won't even notice it in how the entire cable behaves. Plus, it's way easier to create a flexible shape from tens of thousands of thin elements. The cable can smoothly wrap around the towers, forming a huge parabola over the span, whereas a rod of that diameter simply won't bend without plastic deformation. The process of creating main suspension cables is also nothing like how regular steel cables are made at the factory. Nobody sends a finished cable to a construction site that's 3 feet thick and thousands of feet long. That kind of monster would be impossible to deliver or hoist into position. So the main cables of suspension bridges are spun on site. It starts with installing temporary pilot cables between the towers. A traveling carriage runs along them, shuttling back and forth across the entire span. A reel of steel wire is mounted on the carriage. Each trip of the carriage pulls another wire between the shores. One end of the wire is anchored on one side. The carriage holds the reel across the span. The wire is secured on the other shore, and the excess is cut off. Then the next wire, and this happens tens of thousands of times. To keep this insane marathon from turning into chaos, the wires are organized into so-called strands, or sub-cables. For example, several hundred parallel wires are bundled together into one strand of a specific diameter. First, all the wires get pulled tight with a bit of slack. Then, special jacks even out the tension, so each individual wire carries roughly the same load. Next, the bundle gets clamped with rings, or special clamps to keep it from splaying apart. Once you've got enough of these bundles, they're brought together and clamped again into one massive structural cylinder. A spiral wrapping of thin round wire goes on top to hold the shape, plus a protective layer of paint or other anti-corrosion coating. At this stage, the cable can already hold an incredible amount of force. Picture this. Hanging from it is a bridge span, a steel truss or box girder that supports the roadway. This span transfers its load through suspender cables onto the main cables. Every vehicle crossing the bridge adds several tons to the system, sometimes dozens if we're talking about a semi or a convoy of trucks. Wind pushes against the structure's lateral surface with forces that can reach thousands of kilonewtons during a storm. Ultimately, the main cables feel all of this, stretching literally a few inches along their entire length while staying within elastic deformation limits. The beauty of a suspension bridge is that the cable works purely in tension, not bending or compression. That's the ideal mode for high-strength steel. The elastic modulus and tensile strength of these wires are engineered so working stresses stay well below the breaking point, even accounting for wind gusts, temperature swings, and traffic surges. During the design phase, engineers model every possible loading scenario. Both lanes completely packed with semi-trucks, sudden braking, seismic effects. The result is an acceptable range of cable stretch and sag within which the bridge remains safe and comfortable for users. Interestingly, despite the system's rigidity, the main cables aren't absolutely stationary. They breathe along with the bridge. When heated on a sunny day, the steel expands and the cable sags slightly. During nighttime cooling, tension increases and sag decreases. In windy weather, you can notice a gentle swaying of the deck. In reality, the cables themselves are also moving, though it's invisible to the eye. It's precisely this living, flexible behavior that allows suspension bridges to handle dynamic loads better than rigid, overly stone-like structures. Excessive rigidity is exactly what led to disasters throughout the history of bridge building, while controlled flexibility allows the dissipation of vibrational energy. A separate critical topic is protecting cables from corrosion. Steel fears moisture and salt spray, especially in coastal regions like San Francisco. If water and aggressive contaminants penetrate inside the cable, reaching each of the tens of thousands of wires, corrosion can invisibly eat away at the cross-section for years until it's too late. That's why immediately after spinning and compacting are complete, cables are sealed. First carefully painted, then periodically recoated. Modern bridges employ additional systems: wrapping with hermetic tape, filling gaps with dried air or nitrogen, and monitoring internal humidity levels. Regular inspections are conducted, including magnetic or ultrasonic non-destructive testing methods that allow engineers to assess the condition of the wires without actually opening up the cable. All of this is done so that a single thread of infrastructure can serve safely for decades. The Golden Gate's cables were designed for a service life of several decades, but thanks to smart maintenance, regular repainting, and monitoring, they're still doing their job today, holding up a main span of over 4,000 feet. If you factor in other suspension bridges around the world, the picture becomes even more impressive. Hundreds of thousands of miles of steel wire strung between riverbanks, bays, and straits, holding millions of cars in the air every single day. Using main cables made from thousands of steel wires is the standard for major suspension bridges, so the Golden Gate isn't alone here. One of its most famous relatives is the George Washington Bridge over the Hudson in New York. It also has two main cables, woven from tens of thousands of steel wires. The total length of all the wire there is measured in thousands of miles, and each cable weighs tens of thousands of tons, just like the Golden Gate. Similar technology was used on the Brooklyn Bridge, though it's older and combines a suspension design with stays. There, the main cables are also made up of a large number of thin wires, woven on-site rather than brought in as pre-made rope. Today's giants are built using the same principle. Take the Akashi Kaikyo Bridge in Japan, one of the longest suspension bridges on Earth. Its main cables? Made from thousands upon thousands of high-strength steel wires. String them all together, and you're looking at tens of thousands of miles of cable. The tension in those cables? Hundreds of thousands of tons. You see the same engineering playbook in China and South Korea, where they've been racing to build massive suspension bridges over bays and wide rivers for the past few decades. What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would stop, lights would go dark, and space engines would fall silent. And yet, it's so rare that the entire world fights over every single gram. But here's the real kicker. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that'll flip your understanding of the metal holding civilization together. Tungsten is a true engineering phenomenon. Its unique properties let us push the boundaries of what's possible in technology, from deep underground to the heights of space. Its story, a story of endurance and unmatched strength. Tungsten is element 74 on the periodic table, one of the transition metals. It has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. To put that in perspective, that's a temperature where most other metals would have vaporized long ago. On top of that, tungsten has the highest tensile strength of any pure metal at temperatures above 3,000 degrees Fahrenheit. It's incredibly hard and dense, making it irreplaceable for applications demanding maximum resistance to wear, deformation, and extreme temperatures. Tungsten doesn't occur in pure form. It's extracted from ores, with the most common being wolframite and scheelite. Wolframite is a complex compound of iron, manganese, and tungsten, while scheelite is calcium tungstate. These ores, hidden deep in the Earth's crust, are the raw material for all subsequent industrial processing. The world's major tungsten producers include countries like Vietnam, China, Russia, and Canada, which hold significant reserves of this strategic metal. The tungsten extraction process is a complex sequence of mining and metallurgical operations. It starts with exploration and ore extraction from underground mines or open-pit quarries. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep within the Earth. It's tough, dangerous work that demands cutting-edge technology and strict safety standards. Thousands of tons of ore are hauled to the surface every single day. After extraction, the ore heads to a processing plant. Here it goes through several stages to separate valuable wolframite or scheelite from other rock. First, the ore gets crushed in crushers and mills until it's a fine powder. Then various enrichment methods kick in: gravity separation, magnetic separation, and flotation. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The concentrate is then processed at metallurgical plants to extract pure tungsten. It's a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent roasting to produce tungsten oxide. The tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2,000 to 3,300 degrees Fahrenheit. The result is a fine tungsten powder, which forms the foundation for all subsequent products. From this powder, through sintering, tungsten rods, bars, and other blanks are formed. Tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, creating a dense, strong material. One of the most critical applications: manufacturing tungsten carbide. Some seriously tough stuff. These alloys combine tungsten with carbon, plus cobalt or nickel as a binder, creating one of the hardest man-made materials on Earth. They're used to make cutting tools, drill bits, end mills, lathe inserts that can slice through the hardest metals and alloys. Without tungsten carbides, modern manufacturing, metalworking, and oil and gas extraction would grind to a halt. A single pound of tungsten can become a drill bit capable of boring through thousands of feet of rock. Talk about efficiency. Tungsten also sees heavy use in military applications for armor-piercing rounds and bullet cores. Thanks to its extreme density and hardness, tungsten alloys have exceptional penetration characteristics, delivering devastating effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is indispensable. It's used to make filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components that need high heat resistance and electrical conductivity. Because of its sky-high melting point, it's used in the aerospace industry for parts exposed to extreme temperatures. High-temperature tungsten alloys are used in jet engines, turbines, and other devices operating under extreme heat. Alloying with tungsten boosts the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with way less toxicity. On top of that, Tungsten's used to make ballasts and counterweights in race cars, aircraft and yachts, thanks to its crazy high density. It's even a component in some jewelry, because of how hard it is and how resistant to scratches. Tungsten is one of the rarest elements in Earth's crust, which makes mining and producing it especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential resources that haven't been explored yet, the total volume could be significantly higher. That's obviously way less than reserves of metals like iron or aluminum, which really highlights its strategic value. Global tungsten production each year, measured in tons of pure metal, or tungsten oxide equivalent, fluctuates. But in recent years, it's been somewhere between 85,000 and 100,000 metric tons annually. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine this. You could take a worn-out tool that's already served its purpose and transform it back into something brand new, without spending the energy and resources to mine ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is one of the most advanced and efficient processes among all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number. It shows just how valuable this metal is and how much economic sense it makes. Where does used tungsten come from? The main source of secondary raw material for tungsten is, of course, worn-out carbide tools. Those same cutting tools, drill bits, milling cutters made from tungsten carbide. After heavy use, they wear down, lose their edge, or break. Instead of tossing them in the trash, they're collected and sent to recycling plants. Other sources include scrap metal containing tungsten, leftover waste from tungsten product manufacturing, plus some electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of mining ore and initial processing. Recycling dramatically reduces the environmental footprint of tungsten production. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production more green and responsible. Can metal burn brighter than the sun? Sounds impossible. But one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside, yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then, the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1,650 degrees. Inside, the dolomite slowly descends, while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms, That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Every year, the world melts down more than 16 million tons of silicon metal, a material without which modern civilization would simply grind to a halt. It makes steel stronger, aluminum lighter, and solar panels possible. But here's something almost nobody knows. To create just 1 ton of this metal, furnaces operate at temperatures exceeding 5,400 degrees Fahrenheit and consume as much electricity as hundreds of American households use in a month. So why does this silent giant hide a diamond structure inside? And what discovery about silicon will change your understanding of technology if you stick around till the end? Industries use metallurgical-grade silicon as a foundational material for creating ferroalloys, particularly ferrosilicon, which gets added to steel to improve its strength, corrosion resistance, and ability to withstand high temperatures. How steel deforms, its elasticity, and behavior under load largely depend on how silicon dissolved in the metal matrix behaves. Metallurgical silicon is also critical for producing aluminum alloys, where it's responsible for reducing weight and improving the alloy's ability to maintain its shape when heated. For example, in cast aluminum parts for automobiles, the silicon content can reach anywhere from 12 to 14% by weight. Another key application is obtaining purer silicon suitable for electronics and photovoltaics. Metallurgical-grade silicon serves as the starting point for producing polysilicon, which gets purified to impurity levels in the parts per billion range. This ultra-pure material is what they use to form ingots and wafers for microchips and solar panels. Demand in this sector has shot up dramatically in the US over recent decades, driven by renewable energy expansion and the needs of data centers. To put the scale in perspective, manufacturing a single solar panel module that's about 11 square feet requires roughly 6 or 7 pounds of silicon in the form of high-purity polycrystalline material. Metallurgical-grade silicon has additional applications too. It's used in chemical manufacturing to synthesize silicones, which are needed for sealants, lubricants, medical devices, household products, and electrical insulation components. It serves as the starting material for silanes, compounds that act as coupling agents between organic and inorganic materials, ensuring stronger surface bonding in composites. Certain types of silanes are used as part of adhesives and coatings that help extend the service life of structures in humid or corrosive environments. Technological progress constantly raises the bar for metallurgical-grade silicon, since purity, grain size, and consistency of properties directly impact the quality of the final product. In American industry, research continues on optimizing electric arc furnaces to cut energy consumption, as well as on utilizing carbon monoxide byproducts. On top of that, companies are developing ways to recycle silicon production waste to bring part of the material back into the cycle and reduce emissions tied to mining fresh quartz. All of this makes metallurgical-grade silicon one of the foundational industrial materials. Without it, modern electronics, transportation, and energy sectors couldn't keep up their current pace of development. To turn mineral oxide into metal, you need extremely high temperatures and a carefully controlled reduction reaction. This is done in large electric arc furnaces that operate at massive temperatures and consume enormous amounts of electricity. The furnace is loaded with crushed quartz along with carbon-based reducing agents. Most commonly, these are charcoal, coke, or various carbon briquettes, selected to ensure stable combustion and the right reactivity. Powerful graphite electrodes create an arc that heats the center of the furnace to approximately 5,430 degrees Fahrenheit. Under these conditions, ordinary rocks transform into active participants in the reaction. Silicon dioxide reacts with carbon, and as a result, oxygen is removed from the oxide. Gaseous carbon monoxide forms, while pure silicon transitions into a liquid state. The molten material is heavier than the surrounding charge, so it slowly settles to the bottom of the furnace, accumulating as a metallic mass. Once enough silicon is collected, it's released into special crucibles or troughs. As it cools down, the liquid metal solidifies into solid ingots, which are then crushed into smaller pieces that are easier to transport and process further. At this stage, it's crucial to maintain conditions that prevent impurities from oxidizing again or mixing with the cooled silicon. The raw material obtained at this point already has commercial purity of around 99%. This level of purity works fine for ferroalloys, but it's not enough for more demanding applications. Next comes the stage of refining the metal to higher purity. Silicon can be remelted in a vacuum or under an inert atmosphere, using various methods like sorption, zone melting, or chemical purification. The main goal here is to get rid of impurities like iron, aluminum, calcium, and sometimes phosphorus and boron. The impurity content is controlled with precision down to parts per million, because even a tiny amount of foreign elements can seriously affect the electrical properties of the final product. After purification, you get metallic silicon with the characteristics needed to produce alloys, silicones, or even purer polysilicon. The production process itself is energy intensive, so it's critical that the method ensures minimal heat loss and makes the most efficient use of electrical power. Modern furnaces come equipped with heat recovery systems and electrode feed control. This helps cut down overall energy consumption and boost productivity. Process optimization is a big deal here, because on average, making 1 ton of metallic silicon requires about as much electricity as several hundred American households use in a month. The quality of quartz sand plays a crucial role too. The purer the initial silicon dioxide, the fewer purification stages are needed after melting. Quartz with high impurity content can lead to increased energy consumption and greater furnace wear. That's why deposits supplying raw materials for the silicon industry must meet strict standards for chemical purity and mechanical uniformity of the material. Silicon, though it doesn't have gold's shine, is a true geochemical giant, an absolutely irreplaceable element. In terms of abundance in Earth's crust, it holds an honorable second place, losing only to a non-metal, oxygen. This means that, essentially, we live on a massive silicon-oxygen planet. It's hard to wrap your head around this, but this substance makes up a colossal 27.6% of our planetary crust's mass. Just imagine, almost every 4th ton of material we see beneath our feet is silicon or its compounds. It forms the backbone of entire mountain ranges and serves as the building material for countless minerals called silicates. This element isn't just filler, it's the foundation of our entire modern civilization. As a semiconductor, it powers every chip, processor, and transistor inside your phone, computer, and car. Silicon is the gray eminence of our planet and our technological age. Quiet, abundant, but absolutely omnipotent. Its extraordinary purity is essential for microelectronics, making it one of the most demanding materials in the world. If you pick up any rock or handful of sand, you're holding an entire silicon factory. We all live on a massive silicon planet, not just a water one. Silicon could have been super expensive and sparkly, but it chose the humble path of being a semiconductor to run all the world's electronics instead. Why am I saying this? because pure silicon has the exact same crystal structure as diamond. To put it simply, why silicon with the same structure as diamond isn't actually a diamond comes down to two key differences: atom size and bond strength. Diamond is made of carbon atoms, while silicon is made of silicon atoms. Plus, a carbon atom is tiny, whereas a silicon atom is much bigger. Even though both elements form the same spatial lattice, silicon atoms, being larger, force the whole structure to expand. This makes the bonds between them longer and, as a result, weaker. Every 3 seconds worldwide, a new engine block rolls off the production line, the heart of a car that will withstand millions of explosions, temperatures over 4,600 degrees, and operate for decades without stopping. But how do you transform molten metal into a perfect mechanism with precision down to a micron? One mistaken dimension, and the engine will tear itself apart within minutes of operation. Every year, over 100 million of these blocks are manufactured, and each one goes through a hellish birthing process. Molten metal at 5,400 degrees, sand molds that self-destruct, and robots that cut channels thinner than a human hair. But there's one secret the manufacturers don't talk about. A mystery hidden inside every block that determines whether your car will go 60,000 miles or 600,000. Stay until the end. What you'll learn will forever change how you see what's happening under your car's hood. Let's start by understanding what an engine block actually is. It's the foundation that holds the entire engine together. Inside it are the cylinders where fuel combustion occurs, pistons that move up and down, and other critical components. The engine block must be strong, lightweight, and resistant to high temperatures. That's why manufacturing it is a complex process that demands precision and advanced technology. Everything begins with an idea. Engineers develop a concept for an engine that must be powerful, economical, and environmentally friendly. They use specialized 3D modeling software to create a digital model of the block. This allows them to account for every detail and test how the engine will perform under various conditions. Engine blocks are made from different materials, but the most common are cast iron and aluminum. Cast iron is strong and resistant to high temperatures, but heavy. Aluminum is lighter and dissipates heat better, but less durable. Sometimes composite materials or alloys are used to combine the advantages of both metals. After the engineering team completes all calculations, computer modeling, and finally approves the design of the new engine block, the true heart of the future automobile, the most interesting part begins: its birth in metal. The first and perhaps oldest step in metallurgy is casting. A massive shop filled with the hum of machinery, the smell of molten metal, and the glow of high temperatures. This is the foundry, where engineers' dreams become real components. First, a mold for the block is created. There are two main approaches to creating these molds, each with its own advantages. The first, and most common for large-scale production, uses sand molds. This is an amazing, though traditional method. First, they make a pattern of the future engine block, usually manufactured from wood or metal, and it's an exact copy of the block, but accounting for certain features, such as compensation for metal shrinkage during cooling. Then this pattern is placed in a special container, where it's tightly packed with a mixture of quartz, sand, clay, and organic binding agents. This mixture is compacted, then baked or chemically hardened, creating a strong but porous mold. After this, the pattern is carefully removed, leaving a cavity that precisely matches the shape of the future block. The most challenging aspect of sand molds is creating internal cavities, coolant channels, oil passages, cylinder bores. For this, they use so-called cores, separate elements, also made from sand, that are inserted into the mold. After pouring the metal and cooling, the sand is easily removed, leaving the necessary internal channels. The advantage of sand molds is their relative affordability per unit at large volumes and the ability to create very complex internal geometries. The second method, often used for aluminum blocks or smaller production runs, uses metal molds or permanent molds. These are stronger, reusable molds made from steel or cast iron. They're more durable and allow for parts with smoother surfaces and higher dimensional accuracy right from the casting stage. However, metal molds are much more expensive to manufacture, and it's harder to adapt them for creating the very complex internal channels found in engine blocks. Therefore, they're often combined with sand cores for internal cavities. The chosen material, cast iron or aluminum, is melted in a furnace at high temperature. For cast iron, this is typically over 4,600 degrees Fahrenheit. For aluminum, around 3,000 degrees. In massive induction or arc furnaces, metal scrap and pure ingots slowly transform into a glowing, liquid mass that shines bright orange or silvery light. This process includes precise control of chemical composition. Metallurgists add special alloying elements, such as silicon, magnesium, copper, in strict accordance with the recipe to give the future block necessary properties: strength, wear resistance, lightness. The molten metal is constantly stirred and goes through refining processes to remove unwanted impurities that could reduce the quality of the finished part. Finally, the climax arrives: pouring. The molten metal, radiating intense heat, is carefully transferred from the furnace into special ladles, then into the prepared molds. This is the moment of maximum concentration and precision. The metal must fill every cavity of the mold, displacing air and completely matching its configuration. The pouring process can be gravitational, meaning the metal simply flows under gravity or under pressure, which ensures better mold filling and reduces porosity. After pouring, the mold remains for some time, so the metal can cool and solidify. This can take from several minutes to several hours, depending on the block size and metal type. When the metal has cooled and fully crystallized, the next stage occurs. The mold is broken apart. If it's a sand mold, it's simply destroyed using vibration or hydraulic hammers, freeing the newly created metal object. The sand is later collected and partially recycled. If it's a metal mold, it's opened and the finished block is carefully extracted. As a result of this process, we get what's called a rough engine block. It's not perfect yet. Its surface is rough, it may have sand residue or so-called flash, small metal overflows at the mold seams. It doesn't yet have mounting holes and it lacks the micron tolerances required for engine operation. But it's already a real block. Massive and heavy if it's cast iron, or surprisingly light if aluminum, but already with a clearly defined shape, ready for the next processing stages that will transform it into a high-precision part capable of withstanding incredible loads inside the engine. Mechanical processing is performed on specialized computer numerically controlled machines. The large, solid block is secured on a special table. Around it, various tools move, performing their work. Like a scene from some movie, isn't it? Let's start with the most obvious: cylinder bores. These holes must be perfectly round, have precise diameter, and be positioned exactly on one axis, since pistons will move within them. First, machines use large end mills to roughly remove material, creating preliminary holes. It's like carving out a large chunk from cheese. Then more precise tools come into play. Special boring cutters are used, which carefully remove the thinnest layers of metal, bringing cylinder diameters to the required size. This happens in stages, with constant dimension control. After this, cylinder walls undergo honing. This is final abrasive processing that creates very fine, cross-hatched scratches on the internal surface. These scratches retain lubricant, ensuring perfect lubrication of piston rings and minimizing friction, which is critically important for engine efficiency and longevity. Actually, the cylinder surface after this processing feels perfectly smooth to the touch, but under a microscope has the perfect structure for retaining an oil film. Next, oil and cooling channels. These systems that penetrate the entire block are vitally important. Oil channels deliver lubricant to all moving engine parts, such as the crankshaft, camshaft, pistons, ensuring their lubrication and heat removal. Cooling channels circulate coolant, removing excess heat generated during fuel combustion and maintaining optimal engine operating temperature. The internal, complex labyrinths of coolant and oil channels, as we mentioned, are formed during the casting stage using sand cores. But after this, they need to be opened and brought to perfect condition. For this, high-precision drills and mills are used to create inlet and outlet openings for these channels, and also connect them with other engine parts. Each hole must be positioned with millimeter or even micron precision, so fluids can circulate freely. In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended?